Lastly, let us look at example 3, where we have a voltage-controlled current source as well as a voltage-controlled voltage source. In the circuit below, we have a 193 volt independent voltage source, a VCCS where our output is proportional to 0.4 V3. We have an independent current source of 0.5 amps, and we have a VCVS where our output is proportional to 0.8 V5. Now V3 is our voltage potential across our 2 ohm resistor, and V5 is our voltage potential across our 7.5 ohm resistor. To begin, we'll employ our standard 4-step procedure, where step 1 is to construct n meshes, where we have mesh 1, mesh 2, and mesh 3 designated on the circuit as follows. Step 2 is to assign our voltage potentials consistent with our passive sign convention. Note, we're not going to dually label any shared elements. V1 corresponds to a 4 ohm resistor, V2 corresponds to our 2.5 ohm resistor, V3 corresponds to our 2 ohm resistor, V4 corresponds to our 8 ohm resistor. We see that V5 was prescribed across our 7.5 ohm resistor, but it does not adhere to our passive sign convention, and V6 corresponds to our 6 ohm resistor. We'll change V5 in just a moment to make our analysis a little more simple. Step 3 is to construct n minus n sub c KVL equations describing each mesh current. Since we have 2 current sources, we only need 1 KVL equation. To do such, we'll apply 1 KVL equation that bypasses our 2 current sources. And to make our matters a little more simple, what we will do is change V5 to Vx, and then prescribe V5 consistent with our passive sign convention. That is, when we construct our KVL equation, we have the following: minus 193 volts, plus V1, plus V2, plus V3, plus V4. Note our change of V5, plus V5, plus V6. We additionally have plus 0.8 Vx coming from our VCVS. Now Vx is going to be equal to minus V5. Step 4 is to apply Ohm's law to express our voltage potentials in terms of our mesh currents. And we would have the following: 10I1 plus 4I2 plus 10I3 is equal to 193. From our KVL equation, we saw that I1 runs through our 4 and 6 ohm resistor, such that we have 10 ohms times I1. Additionally, we saw that I3 runs between our 2 and 8 ohm resistor, such that we have 10 ohms times I3. Now, when we did our change of variables within our system such that we had V5 expressed in terms of our passive sign convention, we would have 10 ohms times I2 plus 0.8 times Vx, where Vx is equal to minus V5. 0.8 times minus 7.5 times I2 gives us minus 6I2, such that we have a net of 4 ohms times I2. Now, our VCCS provides the following equation. 0.4 V3 would be equal to I2 less I1, where V3 is simply equal to I3 times 2 ohms, such that we'd have 0.8 I3 is equal to I2 less I1. Lastly, our independent current source gives us the following relation. 0.5 amps is equal to I3 less I2. Thus, we have 3 equations and 3 unknowns. If we put this in matrix form, we have the following. From our KVL equation, we have 10I1 plus 4I2 plus 10I3 is equal to 193. From our VCCS, we had 1I1 minus 1I2 plus 0.8 I3 is equal to 0. And from our independent current source equation, we had minus 1I2 plus 1I3 is equal to 0.5. Therefore, I1 is equal to 2 amps, I2 is equal to 12 amps, and I3 is equal to 12.5 amps. To determine the voltage drop across our VCCS, we apply KVL around loop 1, where we have minus 193 volts plus 10I1 plus the voltage across our VCCS is equal to 0. Recognizing that I1 is equal to 2 amps, we have our voltage drop across our VCCS being equal to 173 volts.